Right, so let's get started on the second problem of the day. This one I imagine is going to absolutely destroy me because I suck at tree problems. But anyways, this is LeetCode number 310, minimum height trees. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes labeled from 0 to n minus 1, and an array of n minus 1 edges, where edges I is equal to ai. Okay, so this is an array of pairs, essentially, of edges between nodes. Indicates that there is an undirected edge between two nodes. You can choose any node of the tree as a possible root. When you select that, the result tree has height h. Among all possible rooted trees, those with the minimum height are called the minimum height trees. Return a list of all minimum height trees as root labels. You can return the list in any order. Okay, so it's kind of like saying find the graph that has the smallest maximum BFS kind of thing at each node. So in that case, if BFS is O of V plus E, and we have to run O of V times, or V times, then O of V squared plus VE would be the brute force, or the naive solution. If we just ran a BFS and counted sort of the number of nodes at each, and we counted the number of nodes at each, or the number of edges to reach all of the elements until we basically exhausted the queue, because that would be the height of the tree, right? Starting from the root all the way down to the bottom. Then that would take O of V squared plus VE time just to iterate through all the nodes, not to mention the amount of time that we would need in order to sort of get the nodes that are that have the same height. In the case of the height, I'd probably add the nodes to a min stack. Maybe add the nodes or the BFS results into a min stack and just pull until you aren't until the next value is not the same. The given input is guaranteed to be a tree and there will be no repeated edges. Okay. Honestly, I'm kind of liking that idea of using a min stack along with BFS at every node. But is there a better way that we could do it? Is there a repeat in terms of the work that we are doing in order to achieve that result? If we start at 0, let's say that we had 0. This has height 1, 2, 2, right? So this has height 2 here. When we go to 1 here, and we check the edges, I don't think there's really any information that we can get out of the previous iteration at 0, right? We know that the root, if we root it at 0, we get a height of 2, but we don't really get any good information here. Yeah, maybe there's a better way to do this, but that's sort of what I'm thinking of. I'm gonna go ahead and code it up, I think. And then if it runs too slowly, then that means that there's probably a better way, and therefore I need to go take a look at that. Okay. It's been a while since I've done heaps, so it'll still be interesting. I'll probably have to double check Kotlin or Java documentation. Let's see. So let's get that heap going. Java min heap. Or priority queue, yes, that's what it's called. So we'll say val q or pq is equal to priority queue, and does this take in a type? Yes, it takes in a type. Well, we want a priority queue of a data class that we want. And we want a data class, we'll call this root height, which will have a val root number, which is an int, which will represent n basically, and a val height, which is also going to be an int, which represents, well, the height if we root it there. We know that all the pairs are distinct, and I think given that is the case, it would be nice to, well, actually it doesn't really matter if they are distinct, right? Yeah, no, it doesn't. It doesn't really matter if the root heights in this implementation, if the numbers are different, or if the numbers are the same or not. This will be a root heights, and we need a comparator. We're gonna need a comparator. Which will be here, which will be a companion object, I think. Or actually, override function compare b, which is of type root height. And then we can say when or maybe we can do a class root height comparator. I know that we had trouble with this before, which is of type root height. No, this is an interface, so we can't implement it like that. So I think it's like this. So when this is, let's see. this dot height is equal to b dot height, that returns 0. This will return an integer. When this dot height is less than b dot height, and otherwise, negative number if the first argument is less, and a positive if it's greater. Okay. Which will take a capacity. We don't really have a capacity. We don't really have a capacity, but do we? Well, we will need n elements within here, and then we can just do root height dot compare. We need a comparator. But how do we actually implement a comparator? Such as c dot. Yes. Can we implement comparable? If we do a class root height comparator, which extends comparator, this needs to override the compare function, a which is root height, b which is root height, and this overrides it for the comparator of type t. Override fun compare, or equals a which is root height, b which is also root height, return a dot root number is equal to b dot root number, and a dot height is equal to b dot height, and then this goes here. This returns an int, this returns a boolean. I can do that. I wonder if that will work then. Root height comparator. Let's just return empty list for now, and let's just see if this compiles. This is a data class, so it should have no problem accessing the items. Should have checked the other errors if there were any. Equals overrides nothing. Oh. Something like that. Equals still overrides nothing. And this does not exist. So, I mean, what if I just don't use the equals? Because, I mean, there's no reason. We don't need the equals either, so. Okay, cool. Looks like it compiled. Yeah, maybe some priority queue to study priority queues. Lamau. Anyways, so we have a priority queue set up, or it should be set up, and then we can say for I in 0 to n minus 1, because this is inclusive, we will say we will need a queue this will be a mutable list of int, and this will start with a sorry, let me think. I don't know why it took me so long. We'll start with I, while Q is not empty. So this is our BFS portion. Val front is equal to Q dot first, and then we can do Q dot remove at first, and then we can say for edges dot for each pair, and this is probably follow up, probably mapify int list int in order to speed things up. And we can say var height is starting at 0. And then we can do here, we can do height plus plus if the queue is not empty. If queue is not empty, height plus plus. So basically, if we have new elements within here, after we've popped it, then we can increase the height because we know that this will iterate again. But we want to make sure that there's actually elements in there. The mapify will speed things up because then we don't have to do this linear scan each time. And actually, I'm going to go ahead and do that right now. This will be basically an adjacency list. And this will just be a map, mutable map of int list of int. And then we can say for I in, or actually we do edges dot for each I just realized that we're going to have a problem here where we need to make sure that we don't iterate over the nodes we've seen before. This will probably be a set then, so we can add a scene set is mutable set of int. And then we can say that if not here, then we do that. And this will also start with I, just to make sure. But realistically, we probably want to, let's see. We probably want to add it here. This is more of a visited set, but dot add I, or front, right? Then in here are edges. Going back to the map thing, we are going to say for each pair, we are going to say adjacency list. This will be a mutable list because it has to sort of be. Get or put at pair 0. This will be an empty mutable list of int list. So we either get the value or we put in that, and then we can add to that list pair 1 and clist get or put pair 1 mutable list of int dot add pair 0. And then this should basically add the adjacency list to both of them, because we can go in either direction, right? So that adds our adjacency list into our adjacency list. And then now we can do we can do adjacency list dot get at front, and if there are items in there for each list, or actually we want to do so this will return a list. So we want to do a for each adjacency if not scene set dot contains adjacency dot add, or not adjacency, q add adjacency. So basically we add it to our list if we haven't seen it before. And we really want to do most of this if we haven't seen it. If we haven't seen an item yet. The problem is that we'll probably run into a situation like, so for 0, we'll go here and then we'll add 1 to the list. 1 will add 0 to the list, to the queue again, as well as 2 and 3, right? Well, we've seen 0 before, so we won't add it into the list again. And there's no way that we'll process a node. And because there are no cycles, then there's no way that we will have a situation where we'll process a node before we've seen it, I think. So I think that this is actually fine, that we don't need to wrap this around an additional check. So, height plus plus, okay. So this should do the BFS part, and then we can say pq.add. We want to add I, or we want to add a new root height where the root number is I, and the height is height. Then we can say var min height is equal to pq dot. Is there a peak function? There is a peak function. And this will be the min height dot height, while pq dot peak is equal to min height. So while the top element is still the height, then we want to do a return list return list add pq.poll.height. And then we want to return our return list. So basically, we run through BFS, starting at each node. We count the height of the tree. And then from there, we poll until we cannot get, or while pq.is, is there an empty? Is empty. So while it's not empty, because we don't want to keep on polling until after it's empty, we want to keep on adding into our return list, and yeah. So the main breaking points that I'm worried about is this edges adjacency list here. I hope it doesn't break. And then maybe also within here, within the scene set, I think the logic with regards to the tree still holds, meaning that we won't go back on us. We won't add a node into our queue that we have already seen before, or we won't have duplicate of those. We won't have duplicates of those values. So I think that's fine. And then maybe just some syntax stuff. But let's go ahead and run this. Just do a base run, and let's see where we end up. Edges for each here. It doesn't look like it likes that. If we just do a return here, would that satisfy? Because it looks like it inferred the type as a Boolean, the return type as a Boolean. I guess it counts this as the return type at the end, right? That's sort of how the for each works. Maybe. Then this get or put cannot be applied to you. Mutable list arguments int, mutable list int. This takes in a mutable list. This pair is 0, should be arguments are the same. Oh, this should be wrapped in a lambda. Right. Then this should be front, not first. Let's go ahead and run the code again. Must return a value of list int. Oh, geez. I thought this could return a unit. What? Oh, no. Never mind. Yeah. No, because I was returning from the base function. If this still doesn't like it, then oh, it looks like we're gonna run into a TLE. Let's see. Interesting. I want to print out the adjacency list just to see what it looks like. And I'm guessing that in that case, then we're probably removing something, or we're not doing something right here. Let's see, if we do 0, because we add it here, then the front is 0. We add 0 to our scene set. Then in our adjacency list, we'll see, okay, so we have 1 here. Then 1 is not contained within our adjacency list, so we add it. Remove at 0. And then we add that to our queue, the 1 to our queue. We remove the 0, and then since the queue is not empty at this point, then our height increases by 1. I don't know why. Is it poll? No, poll removes the head. Okay, looks like we're getting some. So 0 or 1 has adjacencies to U, 0 has adjacency to 1, 2 to 1, and 3 to 1. That is correct. This should be not the height, this should be the root number. But why is the min height? Why is the min height 3? Print line root at I has a height of height. Interesting. 0 has a height of 3. Let's see. Should be see. Because we go through here, we add 1, we add 2. 2 adds nothing, but we still have an item in there. Okay. We can do a var has added node is false, has added node is true, and if has added node is true, then we do height plus plus. So now it'll only give us when we have a height there, when we have actually added a node. Let's just keep that print line here, and let's preserve our print line here too. Let's run our examples. Specifically this one, it'll be interesting to see. Okay. So root at 4 has a height of 2. Root at 3 has a height of 2. And let's add a print statement here too. Increasing height. It's probably not very professional to keep these print lines in here, but I think that they're better for readability, and like if I decide to go back and look at these solutions, then I think that they're really helpful. So we add at 3 we add, let's see, at 3 we have 0, 1, 2, 4, and then we increase the height. We add node 5 and we increase the height again, and so the root at 3 has a height of 2. Here we add a root of 3 or node of 3 and 5, We increase the height once, we add 0, 1, 2, and we increase the height again. Yep, that makes sense. Seems like it works. And let's submit, and let's see if there are any edge cases that we did not happen to catch. Let's see. 0, 1, 0, 2, 0, 3, 3, 4, and 4, 5. What does this look like? So 0 is connected to 1, 2, and 3. 3 is connected to 4, and 4 is connected to 5. So I think the root should be 0? No, the root should be 3. Why is it like that? We start at 0. 0 adds 1, 2, and 3. Then 3... 0 adds 1, 2, and 3. Then 3 connects to 4, and 4 to 5, so that would be 1, 2, 3, a height of 3 for that. 3, on the other hand, connects to 4, or 0 and 4. 4 connects to 5, so that's 2. And 0 connects to 1, 2, and 3, that's 2. Interesting. Yeah, this is, this shouldn't be happening. Odd. This isn't even like an edge case, I don't think. I think this is just... So we add 1, 2, and 3. So 0 has a height of 3. 3 has a height of 3, and 4 has a height of 3. Why though? 0 or 3 adds 3 and 5? Oh no, that's starting at root 4. I should really add a print line here and say like root is, or starting height calc of I. Anyways, we add 0 and 4. Then we add 1 and 2. Because 1 and 2 and 5... 1 and 2 and 5 are on the same level of traverse, or on the same layer. So what we can do instead is what I've seen is in the level order traversal of a tree, which is to use a for loop instead, where we calculate the number of nodes that we've added. Nodes added 0. Nodes added plus plus. Nodes added is greater than 0. So, do we wrap the for loop inside or outside? Let's see. I think inside. And what we do is that we do for node index is in 0 to nodes added. What we will do let me think about this some more. So what we want is that we want to poll the number of nodes exactly equal. So we want to check and add the adjacencies equal to the number of times that we have added, or for the number of new nodes that we have added. Let me think. So in that case, if we use a for loop, nodes added, then we say while queue is not empty for node new node index in 0 to nodes added inclusive. Probably do -1 though. Yeah. Then we want to say val front is equal to q.first and then q.remove at 0. Then we want to get the adjacency list. So we want to pretty much do this. So we want to do this, but how do we check? Let's grab all the comments back. How do we add the height? For our new nodes added is equal to 0. After this for loop, we can do new nodes added, and then we can say if new nodes added is greater than 0, then height plus plus, and we can do a print line here, added new nodes added, nodes increasing height by 1. I think that should work. So the idea is that we count the number of nodes that we've added. So for example, on 3, for 3 we add the nodes 0 and 4. Oh, and of course, we do nodes added is new nodes added. So nodes added initially starts off as 1. This should start off as -1, right? because it's 0 to the last value inclusive. So it'll add, at 3 it'll add 0 and 4. And nodes added, so the queue is not empty. We started off with I. This will run from 0 to 0, so exactly once. We add the item, or we get the item at the front. We check the adjacencies. In this case, adjacency for 3 is 0 and, for 3 is 0 and 4. We'll add those new adjacencies. So that takes the new nodes added from -1 to 0 and then to 1. If we do this, this will still run once. I think that's fine. While the queue is not empty, so we know that there's an item in there. This starts off as 0, right? Because then it will... We can set this at -1. So then when we add 0 and then 4 from 3, this will go to 0 and then 1. So that means that the next loop will run twice, which makes sense. And since the new nodes added is equal to 1, which is greater than -1, then we increase the height by 1. Then in the next iteration, we will pop the queue twice, because we have two items, 0 and 4, in the queue. The new nodes added, let's see. So this will go from 0 to 1, which means it will run twice. The first value is 0. It adds 1, 2, and 1 and 2, which means that we added 2 nodes. So this will go to 1. Then it'll run again, and this time it'll grab the 4. It'll add the 5, so now this new nodes added is up to 2. And then it'll, if new nodes added is greater than -1, we increase the height again. So now the height is 2. However, the next time we iterate around, we don't add any items, but it'll run from 0, 1, and 2, which is 3 times, which makes sense because we added the nodes 1, 2, and 5 from the last iteration. Those will check for adjacencies and not find anything. We remove them. New nodes added stays at -1, and therefore we do not increase the height. And then after that, the queue is empty. I think this works. Let's go ahead and run the code. And let's see if there are any errors, compiler errors that we need to keep track of. Or if we run into another TLE. Let's see. Why would we run into a TLE? Starting of calculation of height 0. We add 1, 2, and 3. This is new nodes added plus 1 is the number of nodes that we actually added. So we could do a -1 here. Set this to 1. Set this to 0. Remove this now, basically. I don't think that'll actually solve the issue, but interesting. We have no cycles. However, we did not add back our scene. Set add from. That might be it. Awesome. Let's run through our base example cases. Okay. Let's comment out our print lines because they do cost something. They are IO after all. Don't need our adjacency list either. Let's run a submit and let's see if now we get our proper. We do get a time limit exceeded. So that probably means that this solution is not fast enough. Okay. So that means that this solution is not fast enough, and we are coming up at 52 minutes. So I think that takes us to the end of the line in terms of this solution. I think we had a decent strategy for solving this problem. It just wasn't fast enough. So there must be a trick or some intuition of additional work that we can skip as long as there must be some additional work that we could skip. So I'm going to take a look at the discussion tab, or maybe at the solution. Or maybe I'll just think about it for a little bit more. I might have a couple of things, and then I'll come back. So I took a look at the solution, and it makes sense. I made an adaptation of it. I'm not happy with my understanding of the solution, essentially. The main intuition comes from the fact that within the minimum height tree, there are two possibilities only. We can either have one node which has a minimum height, or two nodes which have minimum heights. And this is provable by a proof by contradiction, it seems. Essentially, the idea is that it's not possible for three nodes to have the same height of, if we rooted it at there. If we rooted it at the node, it's not possible for three of them to have the same height unless there is a cycle. And because we know that there is no cycle, then therefore there must be only either one or two nodes that have the minimum height. From there, we do something a little bit different. Rather than running a BFS from each node, which would be expensive, we instead go from the outside in a sort of topological sort manner, where we get rid of the leaf nodes every iteration, and we add the next set of leaf nodes. Essentially, we continue doing that until we get down to one or two nodes. And that's basically our solution. That way, our runtime is limited from, or is decreased from a polynomial runtime because we have to run BFS at each node, down to topological sort, which is roughly big O of the number of vertices within the graph. Did I see an insect? I have no idea. Anyways, let's walk through my solution. So the three main parts of my solution are the adjacency list, which is a map that maps from an integer to a mutable set. I'm using a set here because it makes it easier, it makes it constant time actually, to remove items from the adjacency list. If we had duplicate integers, then this wouldn't be possible. We have our return list, of course. Actually, we don't need our return list now that I think about it, because we're using our queue, which happens to be a list, and a set of integers that we've seen before, so we don't backtrack on ourselves. We start by creating and building our adjacency list, which will take O of v plus e time, just scanning through all the nodes and all the edges. We then start with our queue, but before we start actually running through our queue, we will add all the leaf nodes as indicated by our adjacency list if they have a size of 1 into our queue to process first. While the queue has at least 2 elements, then we need to process them. The reason why we check if the queue size is at least 2 is because at 2 we have the possibility of either a potential third element that we have not seen yet, being the actual middle, or we could have those 2 nodes actually linked together and those 2 nodes being the middle. We have to check that. We also have a counter for the number of nodes, the new nodes that we've added. This is so we just go in order, and this is so we know when essentially we have a pair of nodes that we need that we can combine together and return. The idea is that after we finish a layer, or at the start of a layer rather, if we encounter another node which only has an adjacency to the node that we're at currently, so if our only other adjacency is a node that has only an adjacency to our node, then we know that those 2 are paired up, and thus we can return them. So that's what happens here. Otherwise, we will go through and we will remove the adjacency, hence why we use a set here, so we can get constant time at this point. We will remove the edge from our node to the other node and from the other node to our node. Pretty standard stuff. Of course, after we've removed the node, we want to check if that other node is now a leaf. If that node happens to be a leaf now, we will actually add it into our queue to be processed next cycle, essentially. And then we'll remove our node. So that's basically our solution, running a sort of modified BFS with a queue size of at least 2, creating our adjacency list, and then running a sort of at a high level, basically running a topological sort, going from leaf nodes all the way to the middle nodes, or middle node, singular. That's how I understand it, but at the same time, I'm still very iffy on it. This is something that I'll have to come back to, and I'll probably have to spend a lot more time off camera to really understand. But in any case, I hope you learned something, and I'll see you for the next problem.